Hey everybody, it's Ripley back again. Today we're going to talk about double integrals over rectangles. Now I'm going to explain what that means, all right? But first let's get an idea of what we're talking about here. So what I have, look at this, I love this snap. Random surface. So the random surface that they're talking about here is this curve here, right? We can't really see the back side of it, but let's just sort of assume that it sort of levels off and heads for the z. So this is going to be my z-axis. As you can tell, there's an x here, and excuse me, there's a y there. Now, this integral that we're going to find when we're taking this double integral, I want to make sure that we understand. It's the volume of all of this yellow space. All right, we're going to be taking integrals, but just like back in Calculus 1, we're going to build out what the double integral really means and the notation associated with it, okay? So, the double integral that we're talking about represents the volume. So let me change colors here real quick so we got it. The volume that we're talking about here is the volume of this solid. Now, hitherto, the only types of volumes that we've really talked about have either been rotational or they've been generated using a footprint. Now, if all that we have is z equals f of x, y, that's floating above the Cartesian plane, and we don't have any association between this region down here and the surface other than the domain, right? Then we can't use that whole footprint technique. Now, I want to define something very clearly, and this is a great example for that. This 2 by 2, so notice this is x down here, and this is why I sort of obscured it. According to what I have here, this goes, x lays between 0 and 2, as does y. Y lives between 0 and 2. And what it does is it defines the domain of the surface that we see. This is often, as is in our textbook, referred to as R. It's a rectangular region. Now, we've seen it before as D. But the notation that we're going to use is going to talk about this rectangular region. So in other words, you pick any point in this bad boy, and you're going to be sent up to a point in z, which is equal to f of x, y. All right? Now, a quick little review of just standard issue integrals. All right? Whoa, that was awful. It'll suffice. All right? Remember how, if I got f of x, and I'm going from A to B, whatever that is, and I'm looking for the area. Remember how back in the day we built rectangles, right? When we first started playing around with this thing. And what did we do with the rectangles? Well, we added up their areas, right? And then we said, all right, if I want the actual integral, if I want to know what the area, under the curve, which equaled the integral from A to B of f of x dx, well, what did we do? We took the limit as n went to infinity of the sum as I goes from 1 to n of f of x sub I times delta x. And if memory served, for those of you who took me for Calc 1, 2, we did this right around Thanksgiving, and we're like, whoa, we can take this home and show people how smart we were, or how smart we are, right? So remember what this was. It was just all that we did is we were adding up a bunch of rectangles. And then how many of them were there? There was an infinite number of them. What was this x sub I? Well, x sub I was just where we started, right? This is an x sub I. This would be like x sub 1. Well, I guess that wouldn't be x sub 1. This would be x sub 1. This would be x sub 3, apparently. And then somewhere out here, as we got more and more and more of these, we could just call something x sub I. And if you remember, it was an arduous task to actually go through this limiting process. Remember when I forced you guys, you hated me for it, when we took the integral from 0 to 1 of x cubed, or x squared, I think it was. It doesn't really matter. And I made you actually go through this limiting process. You had to do it algebraically. Well, hit your knees tonight. Thank your lucky stars that I'm not going to make you do that. We just need a notational idea of what's going on, okay? So we've got this in 2 space. Now the question becomes, how do we do this in 3 space? Now I'm going to use this as an example, okay? But first things first, I want you to understand that in this case, what we're looking at, where R is defined by the x, basically the rectangle created, well, it's a square, right, which is a very specific rectangle, created for x values between 0 and 2 and y values between 0 and 2. So the way that we write that is we would say R is equal to R from 0 to 2 cross. We don't say union because we're actually, this cross is like a geometric multiplication thing, okay? It's between 0 and 2 and y between 0 and 2. So think of this as my x and this is my y. Another way to say this is it's the set of all x, y in R2, right, in 2 space, such that x is between, inclusively, ooh, that's one thing about this pen that doesn't work really well in small spaces, and y is between 0 and 2. Now, if we were dealing with a different surface with different rectangles, then this would be, the general case would be from A to B and then from C to D, right? Does that make sense? Hopefully it does. Okay, now here's the tricky part. So let's look really closely. Let's grab, I don't really know what these blue things are, but what I do want you to focus on, let's change colors. I'm going to grab one of these rectangles in here. Let's grab this guy right here, okay? If you think about it, look at that rectangle. What is the height of that rectangle? Well, the height of that rectangle is f of x sub I, y sub j, right? Do you understand why it's a j instead of an I? Well, i's are already claimed. Our i's are going to sub-index x, and then we need another sub-indexing variable, which we're going to call j. So i's are associated with x, and j's are associated with y. Now, I'm not going to get too crazy on this, but watch let's get a little bit of theory here. Now look at how this thing is set up, which I know is a little bit goofy, but bear with me. Do you agree that the thickness of this guy in that direction along the x is just delta x? And the thickness in this guy right here is delta y. Okay? Can you see that? So what we've done is we are creating a volume of that one little guy. What is it? Well, it's delta x times delta y times f of x sub I, y sub I, or excuse me, y sub j, right? Well, that's not entirely correct because look at our sub-index. What I've got is, here's my problem. Let me show you something. This is going to drive you guys a little crazy. All right. Do you agree that this is my x sub I that corresponds to a specific y sub j? But I could have this could be x sub 5, and this could be let's call it y sub 3. But I've got all of these x sub 5s that I would have to count up because each one of these rectangles is going to have an x sub 5 to it. So I can't just sub-index with x sub I and y sub I. I actually have to think of it like a matrix. It's going to be rows and columns. So what I'm going to have is I'm going to have an x sub 5 and a y sub 1, an x sub 2 and a y sub, or excuse me, an x sub 5 and a y sub 2, an x sub 5 and a y sub 3. So what I actually need is I need to sub-index both of the sets as though I'm filling in a matrix. When you go into 2 space, it can get a little bit crazy. So this is going to be y sub ij. And then we use the notation, remember when we had the little star? Now, what that star represents, we'll discuss here in just a sec. Okay? So this is what the volume looks like. Now, this notation is a little cumbersome, especially since we know that change in x times change in y is change in a, right? It's just the change in the area. True, x times y in this context on the Cartesian plane is just a. So this is going to be f of x ij star y ij star. Remember, don't freak out about this sub-indexing, all right? All it says, it behaves just like, it acts like a roadmap, right? So in other words, since I want these two guys to match up, and I don't want to get confused about where I am, I want them to be uniform. If I'm talking about x sub 2, 3, y sub 2, 3, okay? If I'm talking about that, that means move over 2 deltas on the x and move over 3 deltas on the y, and then get yourself in the middle somewhere, and then whoop, up we go to the curve. Okay? Hopefully that makes sense. Let me go ahead and erase that. That's going to be in my way. All right, now there's a problem. There's a bit of a problem. But before we get into that, I'm going to write out what the volume is approximately equal to. Because if you think about it, this is exactly what we started with back in 2 space. Do you agree that all that I have to do is I have to add up all of these, what would these be? Prisms, right? Right parallel prisms. That's right rectangular prism. Why did I say parallel? Right rectangular prisms, right? So here's the way the notation works. It's a little scary at first, but if you can create sort of an analogous relationship between what I'm about to write and what we've dealt with before, don't be afraid. Now, I'm doing an approximation first, and if you think about it, this is going to smell a whole lot like a Riemann sum. This is the sum as I goes from 1 to m. Now, these are arbitrarily chosen variables, but we want to kind of stay out of our way notationally. This is this is times the sum as j goes from 1 to n of f of x sub ij, throw a little star in there, and then y I j, throw a little star. Remember what that star means. It's where in that little square down here we pick the value that we're going to shoot up to the curve. All right, and then this is times delta A. Now, if you recall, isn't this akin to, I'm going to change colors so you don't think I'm actually saying anything crazy, isn't this akin to things like LRAMs? Remember those? And RRAMs. What is going on here? RAMs, RRAMs, and MRAMs. It must be the way I'm using my pen. Operator error, hate it. All right, so you ready? If I want to get the actual value of this thing, of the integral, all right, I want to know what exactly the volume is under the surface on the region defined by x between 0 and 2 and y between 0 and 2. You can probably see where this is going, all right? But we need some notation first. The actual volume is going to be the limit as both m and n. Now, this is not an ordered pair, all right? Otherwise, I would put parentheses around it. As they both go to infinity of this sum, as I goes from 1 to m, and j goes from 1 to n of f of x sub ij, little starry thingy, and y goes, y sub ij, little starry thingy, and then delta A. Delta A is just the area. Okay. Now, this is an integral, as you can probably well imagine. And that integral, it's actually 2 integrals. We're going to integrate. Can you see why it's 2 integrals? We can actually build what we know about sums and limits. We can turn this thing easily into the double integral over the region. Whoa, double integrals. Those are scary. We'll define them in a little bit. Don't panic. All right. In the meantime, we're just going to add up a bunch of prisms. Okay. Over the region. So we say the double integral over the region R. Remember what R was. All right. That just means we're integrating this z function over this area. Now, if you say it like that, it makes total sense. We're integrating the surface. Where does the surface live? The surface lives over its domain in the xy plane, which we're calling R, okay? Now remember what happens to these little stars when we actually take an infinite number of them. Well, this guy just turns into f of xy, and then we're going to throw in a dA. Remember, deltas become d's. Isn't that awesome? All right, welcome to the world of double integral. Now you may be saying to yourself, how in the world am I going to do that? Like, we had a mechanical way to do this sum. right? Back in the day. Well, how am I going to do this? Well, and your worries are not unfounded because think about it. Before, all I had to do is I had to pick a value somewhere on this subinterval. I had to shoot it up to the function, and then I had to take delta x. And then I found another value, and it could be on the left, it could be on the right, it could be in the middle, it could be anywhere, right? But it was easy. I just shot it up to the function, and then that became the height of my rectangle, and then I multiplied it by delta x, and I just did that over and over again. Well, now we got a problem, don't we? Because instead of breaking this thing up into one-dimensional subintervals of width delta x. Now what I'm doing, I'm just going to use this guy if you don't mind. Up here's 2, over here's 2. Now what I'm doing is, oh look at that, I have a grid to work from. Now I'm breaking this guy up into these little, instead of, again, one-dimensional units, now I have these square or rectangular units. This guy's delta y, delta y wide. And this guy is delta x wide. Now I got to pick a place. Where do I start? Am I going to pick it on here? Whoops. Yeah, let's change colors. That sounds like fun. Sorry, a lot of caffeine this morning, you can probably tell. Am I going to be here? 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 There's an uncountably infinite number of places in this square that I can choose, and then I pick that value and I shoot it up to the function to get the height of that prism. Well, seriously, I think it's pretty easy to see what the solution is. We're going to pick the middle, all right? Just like before, get out of there. We liked the midpoint approximation the best. Remember that as far as the Riemann sums were concerned? We're doing exactly the same. We're not even messing with any other types of approximations, because think about that. I'd have to deal with all 4 of these corners, and I'm not going to deal with all 4 of those corners. I'm going to deal with the midpoint, all right? So what we've got is we've got the midpoint rule. And I'll write that thing down really quickly. This is a quick midpoint rule for double integrals. For double integrals. And this is quick and easy. And you've seen the notation before. We're just integrals. We know that the double integral over R, right? We like that notation because it makes sense. Fxy dA. Now this guy's just going to equal it's going to be approximately equal, because we're doing approximations, to the sum as I goes from 1 to m, the sum as j, goes from 1 to n of f of x bar, all right? And we've got this I, because this thing just cleans it up so much more. Now we don't have to get all awful with this. We just say, hey, we're going to pick the middle of each one. So it's going to be xi yj, y bar, and then this is just going to be, delta a, not dA. We're taking an integral. We're using an approximation, right? Delta a. Now I'm going to do an example for you. It's straight out of the book. I'm going to do it on the next page. So bear with me here for just a second. You ready? We're going to do this example. I am going to approximate the area over the region of x minus 3y squared. And this is going to be dA. And we're going to define R as the set of points x, y. You can follow along in the book if you'd like, but this is one of those I want to spend some time with, okay? And we're going to have x between 0 and 2, and we're going to have y between 1 and 2. 1 and 2. Now, remember our function, f of xy, I'll put it up here, f of xy, which is always equal to z, which is equal to x minus 3y squared. This thing may be a little bit hard to visualize for you. So what have I done? Let's look. All right, what I have done is, whoa, I don't know what's going on here. I've graphed it for you. Okay, so I've got x minus 3y squared, which is what we're playing with. And it's kind of hard to, unless I move it, it gets a little tricky. So here's my x-axis. I've got it between 0 and 2, and here's my y. I've got it between 1 and 2. And then if I move it around a little bit, you can sort of see what it looks like. See, sometimes I have to move them just to figure out what's up. But I wanted you to sort of visualize what's going on. Now, the question becomes, how many prisms do we have to make? Right rectangular prisms do I actually have to make? Well, let's get back to the problem. Again, it's straight out of the book. The book tells me that m equals n equals 2. All right? In other words, so let's write up what this thing is going to be approximately equal to. It's going to be approximately equal to the sum as I goes from 1 to 2 the sum, so this is the sum of the sum, as j goes from 1 to 2. Now you may be going, wait a sec, I thought x was between 0 and 2. No, 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 guys, this is just a sub-indexing set. This is telling me that I'm going to let I roam. I'm going to start it at x sub 1 and let it pop up to x sub 2. I'm going to let j roam over those y's, remember? Back here, well, I won't go back, but I'm going to start it at 1, and I'm going to go to 2. So if you think about that, wait, let me finish this first before I get all crazy. Of f x bar I, y bar j, and then delta A. Okay? Now, we got to figure some stuff out here. What's happening? So I'm going to build, what I'm going to do is I'm going to build a rectangle. Okay? And this thing is going to be, these are going to be my y's, and these are going to be my x's. Okay? However, this thing starts at 1, and it finishes at 2 because it tells me so. This, right? Ooh, I should probably, let's do it like this. Let's do it. I'm going to come down here a little bit, like this. Okay? So here's actually my x-axis. All right? Because x goes between 0 and 1, oh, excuse me, between 0 and 2, and y goes between 1 and 2. Okay? Now, what does this information tell me that m equals n equals 2? It means I'm chopping y up and x up into 2 subintervals apiece. So I'm going to cut it down the middle, and I'm going to cut this guy down the middle. If m equaled n equaled 3, then I would have to cut this thing into thirds and cut this thing into thirds. If m equaled 2 and n equaled 3, then I would have to cut this guy in half and then this guy into thirds, and I would figure it out from there. Now you can probably figure out what's going to happen here. All right? But before I get crazy, just like before, I need to figure out what delta A is. Remember how we had to figure out what delta X was before? Well, let's write some stuff down, just for giggles. I know if x goes from 0 to 2, then this is going to be the point. Let's put some points here. This is going to be 0, 1. This is going to be 1, 1. And this is going to be 2, 1, right? And then if this guy goes from 1 to 2, then I'm just going to label some points so I've got all of them. It won't take very long. Bear with me, please. This is 2, 2, right? This guy's going to be what? 1, 2. This is going to be 0, 2. And then this is going to be what? 0, 3 halves, because 1 1/2. This is going to be 1, 3 halves. 3 halves. And then this guy's going to be 2, 3 halves. Well, how wide is each one of these? How wide, or excuse me, how much area is each one of these? What is delta A? Just like before, remember how delta x was b minus a over n? Now I actually have to compute the area of each one of these little rectangles. Well, they're all 1 wide, right? And they're all half tall. So I know that delta x is going to be 1 times 1/2. Or excuse me, delta A. Ooh, you got to yell at me when I do that. All right? So it's a half. Sweet. Okay. One piece of information I don't have to worry about. Thank God. Here's the fun part. I need to figure out, I'm going to change colors. I need to figure out, ooh, let's go back, where the center of all these guys is, because that's what the midpoint is. That's what I'm doing. I'm adding up all of those values, but I need to figure out each one of these midpoints. So what's halfway between 0 and 1? Well, that's easy. That's going to be 1/2, right? I got 1/2, and then what's halfway between 1 and 3 halves? Well, that's going to be 5/4, right? You know hopefully you know the quickie tricky to get there, right? You see how to do that. Hopefully you see how to do that. You just add these up. 1 plus 3 halves is 5 halves divided by 2. You get 5/4. Okay, now to get from here to here, I can just take the width of the x's, right? So this would be 3 halves, comma 5/4. And then to get from here to here, I can take the width of the y's, which is 1/2, right? Which is 2/4. So this would be what? 1/2, comma 7/4. It's kind of arduous. I understand that. And then 1/2, or excuse me, this would be 3 halves, comma 7/4. Now, I'm not going to go through the whole thing because you would hate me forever, probably more than you already hate me. But I'm just going to write it up. I know that the integral, the double integral over R, which represents the volume, is going to be f of x y delta, dA, is going to be approximately equal to, well, we already know it's this guy. We already know it's this guy. Now all we got to do is write that up. So I take f of the points, 1/2, 5/4, and multiply that times 1/2 because that's delta A, right? You with me? All right. And this is going to be plus f of, where are we at? 3/2, 5/4, and I multiply that times delta A. And to that I add f of 1/2, 7/4 times 1/2, which is delta A, plus f of 3/2, 7/4, where am I? 7/4, and I multiply that by 1/2. And very much like a cooking show, and you can check to make sure, whoops, not approximately equal to, it's exactly equal to. It is exactly equal to, poof, in my, if I use my text, I get negative 11.875. Now, this is the value of an integral, and I get negative. Volumes can't be negatives, right? So what would we have to do? I said that the volume equaled this. Now that's kind of a lie, isn't it? Right? So I got to be really careful with that because all my rules are still in play. Remember, areas were never negative, volumes were never negative. So what I would have to do, and we're not going to get into this quite yet, we're going to get into this in future sections, but what I would have to do is go back to this guy and figure out, wait a sec, is all of this living under the XY plane? It's very misleading because of the way that the grapher puts this thing. It makes us look like everything goes up, but I don't know what Z max and Z min are. So what I would have to do is plug in the values starting at 0, 1 and finishing at 2, 2 and see where this thing lives. Hopefully, this whole thing lives under the Z-axis or under the XY plane. So in other words, the Cartesian plane would be up here because then I could just change that to a positive and I have my exact value. Otherwise, I have to play games with where it changes signs. Oh my goodness, that's good times. Okay, enough said. So you know how this thing works. You can sort of see how arduous it can be. We don't spend a whole lot of time here. We're not going to spend near as much time doing this as we did back in Calc 1. I'm also not going to make you do very many of these because I would have a massive mutiny on my hand. All right, let me do one more quick little issue that deals with double integrals, which is pretty awesome. If we're looking for the average value of a function, remember this guy? You better, because you used the heck out of it. Remember, it was the integral from a to b f of x, I gotta stop saying member, over b minus a. Or you can see this written as 1 over b minus a. And we use this a ton on the AP. It showed up, f of x dx. Now, if somebody put a gun to your head and we had the average value, and we have the average value of f of xy, okay? And they wanted the average value of that guy. And now remember, there's a gun to your head. What would your guess be? How would we extrapolate this into 3 space as opposed to just 2 space? Well, I'm not even going to insult your intelligence. I'm just going to make you think. This represented area, and we divided out. Remember, average value is just a number. It's a value. It's one-dimensional. So here we had a 2-dimensional space represented by an integral, and we divided out the width of the subintegral, right? Now, if you sort of extrapolate this, what would your guess be? Well, I'm hoping you would say, okay, we're going to start with the integral, which gives us volume, right? We're going to take the integral over the region of f of x, y, and we've got dA, and that gives us volume, okay? What do you think? Here's the problem. This is in 3 space. This is in 3 dimensions. It's volume. And I need to get to a single value, a scalar. Don't think vectors, though. That gets a little confusing. I apologize for that. So what do you think you have to divide by? Because we have to lose 2 units. Well, hopefully, you already know what you divide by. It's the area of the region. All right? That's it. That's all it is, which is pretty awesome. And very much like remember how if you recall, if I took the average value and I multiplied it by the width of the interval, I always got the integral, or I always got the value of the integral. Remember, there existed a rectangle that was b minus a wide and average value of the function high that was exactly the value of the integral. Well, I can do exactly the same thing here. If I take the average value of this guy and I multiply it times the area of the region, that would be this guy here, right? Then I would get exactly the integral over r of f of xy dA. I love it. Math's fun. All right, that's enough of that. You guys have a really good day, and I will see you tomorrow.